Now finally we are at the position of understanding those four methods that I have been talking in the last few videos. And keep in mind that, as I explained in the previous video, we are implementing those methods only for these proper rational functions. And those methods are: for an improper fraction, we should carefully see under which category that this improper fraction will falls under. So for those methods or the category, the first one is if the denominator. Now in all these four categories we focus on the denominator, right? So this is the improper fraction, and in all these four categories we focus our attention towards qx, right? Now in the first category, if qx, now from that theorem that we learned in the previous video, we know that qx has linear factors. Like qx can be written as a product of linear factors as well as irreducible quadratics, right? Now the first category is if qx has no irreducible quadratics and these linear factors are distinct, right? Like for example, if we have qx like this, now this is the general format. If we have qx like this, then that means from the first category it says this improper fraction can be written like this. Okay, so we will go to an example. Now here, if we take an example for that first category, which is this one. Now the denominator can be any polynomial, but the numerator can be any polynomial, but say if the denominator is 2x cubed plus 3x squared minus 2x, then this can be factorized like this. Okay, so this is the point that I want to relate with our first category. So even this x can be written as x plus 0, right? And this is 2x minus 1 and this is x minus 2. So now see, we have written qx as this, right? So our qx was equal to this format, which is very much similar to this general notation, or in other words, this factorization can be represented by the general format written above. Okay, and then from this first category itself, it says, now here we can relate this a1 and b1 to the first first term of the product. So a1 is equal to 1, b1 is equal to 0, and this one a2 is equal to 2, b2 is equal to negative 1. Here a3 is equal to 1, b3 is equal to negative 2, right? So we have a direct relationship with this general format in our mentioned qx. Now the special property of this first category is, like, there are two special properties that a polynomial should possess in order to fall under the first category. Those two properties are, it should only contain linear factors, right? And remember, in the theorem that I mentioned before in the previous video, we know that any polynomial can be factorized into linear factors or quadratic factors, or as a combination of, or as a product of both, right? But for the first category, we need everything to be linear factors, but that's not enough, right? All those linear factors should also be distinct. They should be different to each other. See, now in this case, this is the first linear factor, this is the second linear factor, and this is the third linear factor. So those three are different, okay? But if by any chance, if we had a linear factor squared in this factorization, then Qx doesn't fall under this first category, and we will see what we are supposed to do if we have a power. But in this particular case, we need everything to be distinct as well as linear, right? So if so, then what we can do is we can write this product in this format where a1, a2, a up to this point are unknowns, right? Now in our example, we have 3 terms, right? In the general form, I have k terms, okay? Here we have k terms, so we have like k partial fractions, but since in the particular example, as we have only 3 terms, we have only 3 partial fractions, right? So we can, from the first category it says, we can write our improper fraction like this, okay? So what we should do is, if we have an improper fraction, we should check whether the denominator of the improper fraction falls under the first category. That means whether it can be simplified into linear distinct. This distinct property is also important. If it can be written as a product of linear distinct factors, then this improper fraction can be written like this. So there is a method to find this a1, a2 and a3. I will explain it later. And say if from that method, if we have figured out the values of a1 and a2 and a3, then we say this is the partial, this is the partial fraction of our improper fraction, okay? So yeah, this is the way we do our first category. And how about the second one? In the I will go through this example one more time in the next video, and there I will explain in more detail about the methods of finding a1 and a2 and a3, okay? Right. So how about the second category? The only difference between the first one and the second one is here, now remember, we deal only with improper fractions, okay? And here in this second category, we will have Qx as a product of linear factors, but some of them can be repeated. Remember, now in the previous one I said all these linear factors have to be distinct, okay? But in the second category, we have some repeated roots, okay? Say for example, if we have something like this, and this is our Qx, okay? See, now Qx can be written as a product of 2 linear factors, right? This one as well as x minus 3's. Okay, now these are the linear factorization, and there are no quadratic factors, okay? There are no irreducible quadratic factors. But see, now it is true, we can write this one as a quadratic term, okay? Quadratic factor, Okay, like if we write it, if we simplify these two brackets, you will get this one. So it is not wrong to visualize this one as this product also. And here you have a second degree polynomial, but we don't call it as a irreducible factor. Okay, so the least possible way that this can have, like the most fundamental factorization that qx can take is this one. Okay, so to have a quadratic expression in the fundamental factorization, it should be irreducible, but in this case it is not. Okay, right, and I explained the meanings of irreducibility in the previous video. Right, now here we can see that all the factors are linear, but the thing is this linear factor is repeated 2 times and this linear factor is repeated 3 times, right? So what we can do is, so from the second category it says, see, if this is repeated r times, we should write it as a1 over the linear factor, a2 over the linear factor squared and cube up to the rth term. And for example, let's take this one. So there the linear factor of x minus 0 is repeated 2 times, right? So in this case r is equal to 2. That means we should write this like with regarding this x minus 2 to the power squared term, we will have a1 over x minus 0 plus a2 over x minus 0 squared. See, here it says repeated r times and we write a1 over the linear factor, a2 over the linear factor squared 3 times and up to r times. But in this case we had only 2 repeated, like this linear factor was repeated 2 times. And now here it has another linear factor which is repeated 3 times. Okay, so what we should do is, now this is related to rx over x squared is qx. Okay, so we are writing the partial fractions of this term, right? Rx divided by qx. So related to this one you have these two, and related to the next linear factor we should do the same thing, but in this case it is repeated 3 times. So we will have another, now don't write it as a1 once again, okay, because a1 is allocated for this one and these two need not to be equal. So try to write a different symbol. Let's start with b1, and this is b1 x minus 1 plus b2 x minus 2 squared and b3 x minus 2 cube, because it is repeated 3 times. And now let's say, for example, in addition to these two things, what if we have something like x minus 2 times x plus 4? That means, what if the factorization of qx is linear in this way, right? Then it says we have all, like there are no irreducible quadratics, but the thing is this linear factor is repeated 2 times, this linear factor is repeated 3 times, and these two repeated these two linear factors are there only once. Okay, so then what we should do is, for the partial fractions of this unit, in addition to these partial fractions, we have to cater these two individual linear factors also. And since these two individual linear factors are not repeated, for these two linear factors, it falls under the first category. What does the first category says? For the distinct linear factors, we will have this format, right? For each and every linear factor, if it is distinct, we should allocate a separate number, just a digit for the numerator, and we just write it down like this. Okay, so in our second example, since these two are distinct linear factors, we will allocate another two different numbers. So here also you should not write down a variable name that you have used before. Okay, so we'll start with c1, and this will be c1 over x minus 2 plus c2 over x plus 4. Okay, so altogether it forms the partial fraction of Rx divided by Qx. And we have a method to find all these numbers, and I will explain it in next videos, right? So before going into those details in specific, we will try to finish all the four categories, right? Okay, so how about the third one? In the third category, it says Qx contains a irreducible quadratic factor. Now, when it says Qx contains an irreducible quadratic factor, it doesn't mean that it don't have any linear factors. Okay, so it can have linear factors. So if it has linear factors, for those linear factors, we should deal with respect to the first two categories. I will explain it with an example. Now let's consider this one, right? Now we have a certain numerator, which is, and also remember we are dealing with improper fractions, okay? And we have a numerator, and for the denominator, for Qx, what if we have this format, right? Now in the previous two formats, or the two categories, we did not have a irreducible quadratic factor, but in this case you have two irreducible quadratic factors. You can check that p squared minus 4ac condition, and you will see that the b squared minus 4ac term is negative in both these quadratic fractions, so it becomes irreducible. Okay, right? So for this Qx, the new addition, or the new term that we have, which was not there in the previous two categories, is with this quadratic terms. Okay, so what we should do is, for these quadratic terms, we should allocate a partial fraction of this format, right? See, in the previous case, when it is linear factors, we allocated just a number, right? So here A3, or all these A symbols, capital A, capital B symbols represent numbers, right? But when you have a quadratic expression or a second degree expression, we allocate a first degree polynomial in the numerator. So this is the method that we adopt, right? So what you should do is you have to be familiar with this method. Okay, right? So in this case, we had two irreducible quadratic factors. Now keep in mind that these two quadratic factors are not equal, and I will deal with the case when they are equal in the next category, right? So for the time being, we should consider the case where it has got distinct irreducible factors. Okay, so if that is the case, for this irreducible factor, that is x squared plus 1, we should allocate a certain polynomial, first degree polynomial, and for this irreducible factor, we should allocate another first degree polynomial, and also we should find these a1s, b1s and these digits. Okay, there is a certain method and I will explain it in the next video. Okay, so we are just learning the method of writing down the partial fractions. Okay, and for this portion, or I mean this, for this quadratic factor, the irreducible quadratic factor, we allocate a separate first degree polynomial. Okay, and how about these two things? See, these two things are linear factors, and this linear factor is not repeated, but this linear factor is repeated. So if it is not repeated, that falls under the first category. So you just write down those non-repeated linear factors like this and have a digit allocated, just a digit allocated for the numerator, right? So what we should do is, for that non-repeated term, we have, now as we have used a1 and a2, I will name it as a3. We just allocate a digit and you write it along with the given non-repeated linear factor. And this one, for this factor, it is of course a linear factor but repeated, right? And therefore it falls under the second category, right? So what did we do in the second category? We said if it is repeated r times, then we should start from 1 and go up to the rth term, but in the numerator we just mention a single unknown digit only, right? Okay, so since in our example, since this is repeated twice, we just write x plus 3 and this becomes x plus 3 squared, since it is repeated twice, and we just allocate numbers in the numerator, right? Okay, and finally we go to the case where it has repeated quadratic factors, right? Say if we take the same example as before, but with the small change. Now see, here we have two linear factors and one is repeated, and here we have two irreducible quadratic factors, but one is repeated in here, right? So what do we do for these three terms? For this non-repeated for this non-repeated linear factor, we just allocate a number in the numerator and write it down like this one. For this repeated linear term, we just have two terms. We just have, again we just have a number allocated for the numerator, but since it is repeated, it falls under the second category, and we write down it like this. Okay, and for the non-repeated irreducible quadratic factor, it falls under the third category, where we allocate a first degree polynomial with these unknown coefficients, right? So since it is non-repeated, it is x squared plus 1, and we allocate a first degree polynomial, right? And then this is also a irreducible quadratic factor but repeated, right? So how do we handle that one? It is almost the same as it was in the case of repeated linear factors, it's like if it is repeated r times, then we should start from 1 and go up to r. But now see, in the second category, when linear factors are repeated, we allocated only a number in the numerator, right? But here in this case, when quadratic factors are repeated, we allocate a first degree polynomial in all these portions, right? And the denominators will start with 1 and go up to r, where this irreducible quadratic factor is repeated r times. And in our example, this is an irreducible quadratic factor which is repeated 3 times. So we write it down like this one. This one, right? So see, it is repeated 3 times. So we start from 1, 2 and end at 3, where we have allocated a first degree polynomial in the numerator with unknown coefficients. And when representing these unknown coefficient, be careful not to use any variable names that you have used before. Okay, so all these variable names should be distinct because they does not depend on each other, right? And in the next few videos, I will explain you one more time about the method of finding. Like, I will go over these examples one more time and we can discuss the methods of finding these A1 and A2 values. So here what the summary that you should have is we are dealing with improper fractions, and for these 4 categories, first we should look at the denominator, and depending on whether it has linear factors, quadratic factors, and whether the linear factors are repeated and whether the quadratic factors are repeated, or whether we have all those categories, we allocate a separate portion. Now see, in this final example, it has all the 4 categories: linear factors, linear factor which is repeated, a quadratic factor which is not repeated, a quadratic factor which is repeated, right? So all those four categories were there in this final example that I wrote. Okay, so depending on that nature, by following these 4 categories, we allocate a partial fraction accordingly. Okay, so that's the idea you should get, and that's the practice that you should have to find the partial fractions. Then in order to calculate these unknown terms, it's just a matter of doing a very simple calculation, which I will describe in the next video.